go into that? Yes. Okay, so we will show you. Uh, I'm going to go back to the original mic because even if it's low, you're talking to yourself. Yes, I am sorry. Okay, all right. Oh dear. Oh, epic failure. What I was saying to myself just now was that in the previous videos we were not seeing the tracks. Almost half of the tracks, it was like they were blinking in and out. And by going to 60 frames per second, it would appear that we are capturing most of it. And also the problem that I mentioned whilst I was talking to myself again. Can you hear me now? 5 out of 5. Okay, I might be low in voice, but I'm sorry. Okay, so in the previous video where we were talking about these tracks, there were gaps, and we didn't know whether the gaps were because of rolling shutter or because there was genuinely the thing was blinking on and off. By going to 60 frames a second, we've removed gaps. I've also developed a technique to link subsequent frames together in a video sequence, and what you're looking at on your screen here is very long tracks, and maybe I can zoom in to a level where I can show you where there's a break. So here, what you're seeing where I've got my mouse right now, that is a break between one frame and another, and the JPEG or the motion JPEG or the H.264 or whatever is causing this artifact here as it's trying to encode it. So you still see artifacts between the start and the end point, which you wouldn't get if you were doing certain other types of recording, i.e. you're capturing four uncompressed. So, and that's actually possible with one of the capture cards I've got here. However, I think that this gives you a certainty. We can say with certainty that the track that's starting from up here near my face from the anode and is going down and going away into the distance. So it appears like the frequency is increasing. In fact, it's going away. It's almost going a little bit across the camera and then down towards the cathode. This kind of implies that you might think that this has a positive charge because it's coming away from the anode, and it's definitely got some sort of vibration going on there. Now, in the same sequence that has been captured here, it's going to have this glitch, yes. So I'm going to have to sort this out, and I'm glad this is just a quick look-see, this video. And I will come back with a different video on another day when I've sorted out the audio issues. But anyway, you can see on here that there are some straight tracks like over here, and this one that comes out of here and then it goes around and then changes direction. I think what happened is this is more kinetic. It's come out, it's hit part of the cathode, this brass, and then it's gone off in a straight line. But what I'm saying is that we have straight lines in the same frames as these wiggly lines. And more interestingly, we have this structure down here, which I have blown up down, not down there, down here. And this is a 14 times expansion of that. And you might consider, if I get rid of my ugly mug over here, get rid of my face, you can see a little bit clearer, because I'm not in the way, that is, I don't know. Would you say that this is a spiral? Would you say that this is a spiral? I don't know. I think it probably is a spiral. It certainly gives the impression it is. Now, is this point here an artifact where it was between frames? I think it probably is. And so I think there's maybe another one up here. This is made of several segments again. So this looks like it's doing something very different here to here, here, and here, but actually I think it's doing the same thing. You're just missing it because of the way that's within a frame. And then down here, we've got a blow up of this particular trace here. This is more of a spiral. And you can see that it's bright here and dark here, bright here and dark here, bright here and dark here. And you can imagine that this is coming towards you and going away from you, coming towards you and going away from you. And that you might then consider, you know, when it's coming towards you, it's kind of like it's pushing the ions in front of it. And it's kind of bunching up, so it's brighter. And then as it's coming away, they're pulling away from you, and so it's getting darker. So this would imply to me that it could still be just going side to side, but the plane of side to side movement is into and out of the camera. So it's not utterly conclusive that it is a spiral. But I would say that probably this one here, other than this artifact where I think two frames are joined together, and the encoding has just created this artifact, certainly this part round here is a spiral. Now, sometimes you see something is going fairly straight, like over here on this part here, we've got it kind of straight, and then it goes into a spiral. It kind of like changes mode. And the interesting thing is we see these kind of things with strange radiation. Over here, you've got something that's absolutely bonkers. It's going in all kinds of directions. Now, this is not the first time that this kind of behavior has been seen. This kind of behavior has actually been seen and recorded and discussed by Ken Shoulders, and it was in his book, E.V. A Tale of Discovery, in 1980. Well, the images are from 1983, and I may go and show you those. The other thing that I think is of interest here is what is going on the anode. Now, this isn't obvious if you look at an individual frame, but the same technique that I used to join all these frames together to create these long tracks, that has caused this to be highlighted. And what you have are these bright bloom areas and then these tracks. And do you know what this reminds me of? You know what this reminds me of? It reminds me of the Vega Valley. It reminds me of this. So, is this the kind of thing that's going on, but on a much more macro level, that produced the Vega Valley? You actually have these self-organized, I believe, well, they're like, but they kind of attract and repel. But you've definitely got these brighter areas here, and then these tracks, and then these completely dead areas where nothing is going on. This definitely, to me, looks like, in my view, a magnetic fluid. And I think when you see the Vega Valley material up close, and I'll go through my discussion with it, I think we can safely conclude that that's actually what it is. And what we have seen, for instance, in the last video, is we saw maybe my audio is going to go funky again. Let me know if my audio goes funky again. Dear. My audio goes funky again when the cameras. I'm very sorry. If you remember, there was a plasmoid, a big ball of lightning, this self-organized structure. And out of it, we had what I said feel is a kink instability. And this would imply to me that it's starting from a magnetic pole and going down to a magnetic pole. And you've got your magnetic flux going from point A to point B, which means on the outside of the plasmoid, it's not just a simple structure. It actually has a mesh-like nature, and I will go into that in much greater detail. And I believe that explains what you are seeing on the Vega Valley, and what I think you are seeing here on this anode. Now, bear in mind, it is the cathode that was the Vega Valley by Henk, and this is in Dave's experiment. Okay, I've got two mics on, so let me just kill that, and let's kill that. Does that sound better? Okay. All right. Okay, I'm going to... just bear with me. Look at the pictures. Okay. So I have another image, so I'll just go to my mugshot and I will find that one for you because I think you'll rather like it. Okay. So okay. Sounds good again. I think what we're listening to me on now is I think we're listening to. Is this voice? Is this voice both in sync and in what should we say, the right pitch? Oh, no. Okay, all right. Okay, is this the low pitch? Is this the low pitch? Oh God, I think I'll go away and come back tomorrow. Yeah, okay, maybe the echo's gone. Okay, do I sound like Barry White now? Do I? Is it just good because there's no echo, or do I sound like Barry White? It's high pitch now. Higher pitch now. Okay. All right. Okay. I'm going to stick with this. And I think probably it should have an okay audio on this one as well. So, all right. So, I'm going to find you the image now. Okay. I don't have an audio monitor here. Oh dear. All right. Okay. Let me show you this one. It's a little low. It's fine. Okay. So the next frame that I'm going to show you is absolutely stunning. It has a range of different tracks on there and a range of different behaviors. But I think what you're seeing is showing a phenomenal selection of behaviors, many of which were described by Ken Shoulders. So let's see if my audio. Okay, all right, here we go. So there we have it. This is pretty intense, I can tell you. What you're seeing here, in this area here, which looks, I'll switch my mouse, this area here, the reason you've got these overlaid areas is that the plasma bloom here is moving around, and the method that I use to merge the frames together actually causes some sort of fading on subsequent bloom areas, but it captures all of the detail in the major tracks. Now, first off, we've got tracks that go in random kind of directions. So we've got a track that comes up from the bottom here, comes around, takes a hard turn, and comes round over here. We've got one here that seems to go round and bends round this other track. Is it doing that? I don't know. This is where you need to see the frame by frame video, and maybe we can get to that. Maybe we can't because of curfew, but or because of my voice. But this looks like it's coming around this one as it's going through, and it's kind of dinking round and then is going to in a different angle, and maybe that would account for some of these extreme movements that you see these particles do. But I think my two favourite tracks on, well, there's one down here which I rather like. It's kind of going straight and then it just gets to this point and then goes into a squiggle. This one, which comes out of this bloom here, changes direction. And again, it might be changing direction because of other tracks. And so there we go. This one for me, it starts off from the bloom, comes down here, but it definitely starts to go into a spiral here. But here is, for me, the two beauties. It's this large one here, this one here, and this one. I'll go to the large one, and if and when I can show you a video of this, you will see that there's this large bloom down on the bottom right. And what happens is it produces this thing which is moving much slower than some of the other tracks. And we know it's moving slower because in 1/60th of a second, it has this segment here, it has this segment, it has this segment, and then this is part of 1/60th of a second. These sort of artifacts that you see here are where it's joining one segment to the other using the technique that I'm using. So it almost looks like there's a bit of an afterglow, and it might actually be the case that there is a trail behind this that is causing it to be both in the previous frame and in the next frame partially. So you get an intense overlap at this point. But this is going much slower, and it's also twisting. This is, for me, absolutely certainly a dual Evo. And what happens after these segments here is it collides again with the cathode. So it's come from the cathode, it blows out, it corkscrews around itself, double helix type thing. And then it comes down to this point here, and it explodes. And the plasma focus from between the anode and the cathode shifts to the new location where this blob ends. So whatever it was carrying was certainly enough to excite the area over here and change the shift of attention between the two electrodes. Then there is this track. Now actually the direction of this track here, and let me get this all in frame. The direction of this track is from over here, down in the bottom right, and it's coming towards the anode. Now, one might think that it is, it's coming towards where the anode is in the foreground. However, it looks like it's changing its frequency to be tighter, and to me this would imply that it's going into background. So whilst it starts up here, it seems to not changing very much its width, but it changes its pitch, and it seems to have a subcomponent which is, again, appears to be a little bit like a double helix. Now the question is this going side to side and kind of bouncing along a kind of straight line, or what? Is this really a helix going around each other? It's got a curve on one side here, and it has this sharp point here and a sharp point on this one. Now, I don't know if you remember in the previous video, I showed you a paper where they looked at a flux loop, and they were showing the positive charge and the negative charge spiraling around each other, and the magnetic field lines twisted around that. I'm wondering if what you're seeing here isn't one side of this positive and one side of this negative charge, like filament, spiraling around each other. And the reason you're only seeing this here, now I actually have a blow up of this, so you can, this is a 12 times blow up. I'm wondering if what you are seeing here is it's spiraling around. So if you can imagine, it's going from the bottom right down here all the way up to my face up here where the anode is. Now it might not be going to the anode because it looks like the frequency is increasing, and that would imply to me that it's going into the background, and the perspective is away from you, so it looks like the frequency is increasing, but it's actually not changing its frequency. However, it has this one side that appears to be only bright when it's coming into, and I can tell you it's spiraling or shifting left and right, but I think it's spiraling towards the left as it goes to the left. So if it's coming like that, it's from the bottom right up to the left, top left. And so if that's going like that, it's going like that. It's basically going anti-clockwise. I think it's going anti-clockwise. We can check that. I think it's going anti-clockwise. So when you see this bright spot here and this bright spot here, that's when it's coming towards the camera. Like I said earlier, as it's coming towards the camera, there's like a bow wave in front of it. Now, if you are in a plasma with a lot of free electrons and ions, you can imagine that if you had a positive charged filament on one side and a negative charged filament on the other, that the negative would attract the positive ions, and the positive would attract the electrons, as it were, or negative ions, if that's a prevalent thing in there. And so what I think you're seeing is one of these is constantly attracting light mass things. So possibly the line is the positive. The actual one that you can see all the way through here is the positive. And that is attracting electrons. They're much lighter, and there's plenty of them in the plasma there, and they're going towards it. And there's maybe some condensation on, I don't know, but that is causing the glow as that condenses down and it's releasing photons. The other one is the negative. And as what's happening is as it comes towards the camera, it's pushing a bow wave of electrons in front of it from Coulombic repulsion. It might be attracting positive ions, but as it's pushing those electrons in front of it, it's creating some compaction and some heating up. And so you only see that part of the double helix when it's coming towards the camera rather than going away, as we saw in the other one where the helix just got darker in the background and so forth. So this is my hypothesis for now. I would be very interested when I share all the videos that produced these segments. Now, they are gigabytes and gigabytes. So what I'm going to do is I'm literally going to use this phrase I absolutely hate. I will upload the whole video to YouTube, but as I say, it completely mashes it. And there's many videos. What I can do is I can scale it to Ultra HD, and then the 420 in YouTube's encoding algorithms will encode it, and it'll encode enough good pixels at Ultra HD that when you view it at HD, you will hopefully get the resolution back that I'm able to see. But what I'll do is I'll take out all sections of the video that have all these tracks in, and I will then concatenate them into one video at real time with maybe a title frame between, and then I will then play them back at say 1/30th of speed, and then have that as a download which you can then study without any loss of quality. So that's kind of what I expect. So this for me has some stunning revelations in it, and I think you can study this image at your leisure. It will be put into the blog, and I will try and put a GIF image in there as well. And then I want to talk about some other dual camera shots. So there was a suggestion by someone, I'm sorry if I forget your name, someone suggested doing a dual camera, and that was done, and we have some footage from that. There's a lot, and like I say, I need to go through it, but I really wanted to show some of these large macro helixes going on, like this one and this one. And I've got another one here, which is the title frame of the video that we're looking at here today. Now, what's going on here is you've got some brass plates down the bottom, and there's a gap, a small gap between the brass plates, and it would appear that whatever this is being formed as the gap is highly excited, and then it's producing this thing. Now, is it a side-to-side movement? I don't know. It really does look a lot like a spiral. Maybe it's a spiral, I don't know, but it really does look a lot like a spiral in my opinion. So I'm going to change this camera. Sorry if the audio goes, but I think it should be okay. What I will try and do is get some other images that I have here. So this is this essentially a GIF anim, and you can download this GIF anim right now from remoteview.icu from the blog, and you can actually see the track being formed. And this is with each frame taking half a second, so 60 frames a second. So this is divided by 30, and it definitely comes from that center point. I'm going to choose another image now. And I'm going to step through it. Okay. In theory, I can show you this. Okay, all right. So that one. Okay, so this is a 2-camera shot, and I will probably lose my mugshot because that's just going to get in the way. It's a 2-camera shot, and if I do that, you still get the audio. I don't know. Anyway, it's a 2-camera shot, and what it's not ideal. If I go back here, what you would ideally want is a top-down camera shot and one from the side, maybe somewhere either above the cathode or in between the cathode and the anode. What this is it's kind of 2 top-down shots, and it's basically what Dave had available already in his tank, as I understand it. And so what you're actually looking at when you look at this video here is you are looking at the behind and in front of the electrode. So where you're seeing here, this is behind, and it's masking this actual plasma glow quite nicely. And so we will step through this. So let's see. So you can see here on the left-hand side, which is it's sort of in front of the plasma, you can see a track coming out, and over here on the right-hand side of the frame, you can see the same track coming out. If I step forward another frame, you can see, not so clearly probably, there's another track up here, which is this one over here. Okay, it's not so clear, but it's coming out of here, and then this one has progressed over here, and you've got that in both frames. Here again, you've got it up there and over here, and the one that's coming out this side again, this is clearly a spiral. This is clearly a spiral, and so is the one out here, but there are different frequencies. This is a slower spiral than this one, and you can see that you've correlation between the fast-moving spiral and the fast-moving spiral. Now, the interesting thing is that the actual track length is quite similar. The one over here, you know, this one in the bottom right over here and the top left up here, it has one, I don't know, 1, 2, 3, 4, but it's not much different in length in that 60th of a second. But I think it's like, this is almost one full cycle on this one here, one full rotation. And this is like 3 maybe. So this is almost half lambda, and this is 1 lambda and a half type thing. So you can see here, again, very clearly, this one now is very clearly a spiral coming out here. So we step back there, step forward, step back. And you can actually imagine that the one on this side is born in this crack between these 2 plates, and the one on this side is born in the crack between these 2 plates. So it could be that between the cracks, between the cracks in the in the brass, which is what led to this. You see, so this black area here is the crack. There was a piece of brass on here. Sorry if I can see what I'm doing. Between here and here, there was a piece of brass. Between here and here, and there was another piece of brass between here and here. And so between these two pieces of brass, these tracks were formed. And so it could be that some sort of electron bunching, some resonance is going on between that little crack between those two pieces of brass. And that is what is causing enough of a build-up that's maybe causing it to electron bunch to the point of coherence. And that is spitting out these structures. So gaps, cracks, prominences, holes, these are all the kinds of things that might lead to the production of enhanced production rates of EVOs. And it might be worth considering trying to work out what the cracks are and actually taking a brass plate and drilling or milling grooves of different widths, or even a groove that gets slightly larger and larger and larger and larger, and then see where at different energy inputs you get a particular emission, and is it a different size, is it a different frequency? So there's lots to think about, and you can take this a very scientific approach with this. So we just step forward and back a bit on this one. Now, if I quit this, I actually have captured this whole track, and you can see it here. Okay, and if I go here, so you can see it here. I can actually zoom into this, hopefully, and show you. And you can really see that is a spiral going on there. And again, with this, you can see here, and you've actually seen the animation now, so you know what I'm talking about. This is the end of the first part of the track. This is the beginning of the next part of the track. And what this implies, actually, is that there's no real trail behind this. This gap here, and this is an artifact caused by the JPEG compression. And again, you will have one a little bit further up, and after a while you can get to recognize where they are. There's one up here, there's an artifact here. So you've got an artifact here, and you've got an artifact up here. And similarly, over on the other side, there will be an artifact. So you've got an artifact here, where it seems to be breaking and so on. But clearly, this is a much lower frequency spin on the right-hand side. And that's corroborated by the other camera, where you can see over here, this is the fast spin track. This is the fast spin track over here. And coming into camera, and you can see again where there is an artifact on the break point here. And then the slow spin track on the other camera is up here. And I've actually blown up a couple of these tracks so you can see and get a better idea what is going on. So this is one of them. So that's a little bit of a blown up section there, and this is the other one there. And that needs to have a different background to show properly. So that is a different one. Now, I want you to consider something. And I'm gonna prepare this, and I'll see if you can still hear me. Yes, global CCD will be great, and also to have that into a capture device that's doing 444 and is just laying down 444 frames uncompressed. And then we won't have any glitches. You won't have any question about rolling shutter causing any wobbling, although I think it's conclusive enough from these frames that where you've actually got in the same frame straight lines and wobbly lines and in the same kind of domain area. So some of them are behaving differently. There is a different behavior, and some of them are dual EVOs and some of them are single EVOs which are still spinning. Okay, so let me see if I can pull this up. Talk amongst yourselves. Okay, this is truly, truly stunning what I'm about to show you here. And it's just such an honor to be able to have been able to work on these. Really, I thank the guys, and there's so much more to come. It's embarrassing, really, and this is why I'm willing to put it out as horribly raw as raw as this is in terms of presentation standard. It's not something I would like to do, this kind of level of presentation, not ordinarily. So. Okay, see if you're in the room. Can you see that? Right, so again, this is a dual shot, and I don't know if you can work out in your head what's going on, but down here there is a coil of metal, and that same coil of metal is over here. So it's almost just the camera's shifted and rotated. So, but anyway, they are different cameras, trust me. And you'll see something quite breathtaking in a minute. And so I will step forward on this, hopefully. So we've got a blue mode here. Now, what I asked David to do was to use an old film technique, which is the manual equivalent of the clapperboard. So you have a clapperboard and you use that in film. And what am I talking about with clapperboard? Let me see if I can find what I'm talking about. This is a clapperboard, okay? And what you do is you go like that, and then what happens is that the camera, whether that be an old cinema camera or a wet film camera, and all of the audio, you actually see the clapper hit together, and then you have the sound recorded on all of the sound recording devices. So all of your cameras see that, and all of the sound devices hear that. Now, obviously, David didn't have a clapperboard lying around like for some reason I have, and so I asked him to clap. And what this does, ideally, you clap midway between the two cameras. When you're working at 60 frames a second, the cameras aren't gain-locked, which is a term used in television to sync cameras together, which is something you can do with certain types of cameras. But anyway, they're not actually synced together. The frames won't necessarily start exactly at the same time. And so you might have some slight offset, and the maximum offset at 1/60th of a second is 1/60th of a second. So, but the sound will get you within a portion of 1/60th of a second. So let's go back to the audio here. The video, and I'm going to step through. Now look at this beautiful spiraling track here. Absolutely beautiful. Now I have got this merged together at full res, because what you're actually looking at here on your 1080p YouTube compressed stream is two 1080p frames side by side, and so you're actually getting half resolution. I'm sorry, but you'll have to trust me at the moment that this is a spiral on here, and you can see it from both angles. And it's almost born between the crack you know, those two plates sitting on top of each other. Okay, and then we goes again, and look at this spiral here in this right frame. You can see it's over here, but the JPEG is being killed on this one. But over here, this is the advantage of having multiple cameras on the situation. One looks like a bunch of glitches in JPEG because of compression. The other one actually looks like a real spiral. I mean, it's like a pulled out spring. And so you can see it then in the next frame up here, and then tailing off, and almost it's going down at this point. Now, what happened at this point? Was it influenced by this structure coming up here, this wiggle? I don't know. But it changes direction and goes down. Now, I will show you the image of this as a composite shot. So, what you can see up here is the left-hand frame, and now you can see, I'll get rid of my ugly mug so that you can see it clearly. Okay, again, this is clearly in my view, this actually may be a dual spiral with one side brighter than the other, like we've seen before, and they are spiraling around each other. And the reason it kind of goes, how should we put this, fatter and thinner, if you can imagine you've got two Evo blobs, and as they're traveling up here, they're spinning around. It goes thin when they are like in alignment relative to the camera. And then as it goes out like that, as it's traveling up, it then gets fatter, okay? But it looks like one side is less bright than the other, and this is something that we have apparently seen before. And you can see up here that the JPEG part of the compression on the camera, given with the intensity of the bloom here, means that the psycho-visual process of encoding has caused that to just block out. But if we go to the other camera, we can see the left one is less beautifully resolved, but this one is much, much better resolved. And as you can see, it goes up, spirals, and then it just hits here. And when you actually see this on the video, it spends a bit of time doing something at this point. It's like it's not exactly sure where to go, and then it comes down here, and it almost seems like it's changed frequency down here. Now, I have got a blow up of these, so let me see if I can look at the blow up there. So this goes to show the importance, the extreme importance of having multiple cameras on the shot. Really, really important here. So it is a blow up of the left-hand shot. And again, what you are seeing at this point here is an artifact, because this is the first trace, this is the second trace, and I think the third trace might be off shot, but this is the join between two frames. And so it's kind of messed it up. This is not what happened in reality. This is an artifact. Okay? And then we have the other one here. And so you can see spiraling up. It does something up here. It goes all kinky, twisty, and so on. Gets its knickers in a twist, as we might say in the UK. And then, is it changing its spin, or is it just changing its direction? It's definitely changing its direction at this point. Okay. So, to summarize, yes, more cameras is better, and thinking about the location of those cameras can make a big difference. So here's a number of tracks where we've got multiple cameras. Now, I don't really know where I want to take this. I've got so much material, but I just want to highlight something that is from a long time ago, and I don't even think it was recognized by the author. But it's in a paper that was produced by Ken Shoulders, talking about propulsion technology using exotic vacuum objects. And this is about rectifying mass. So when you package material inside an exotic vacuum object, it, as we discussed, loses its mass and inertia. Whilst it's in a white state, it is still charged, but it can be charged at a much lower level. But the mass and inertia of the material inside is masked. So you can use the charge to accelerate it. Then it can go into what's called a black state. Now, in the black state, it does appear to have some controllable properties, maybe magnetic, but to all intents and purposes, it almost looks like it doesn't exist. But then it can be re-excited, and then it can impart the impact of all of the material that was captured inside it. And it's almost like you have the momentum of all of the matter that was captured inside it, but you didn't need to go to the effort of accelerating it with within the right amount of energy to accelerate that amount of mass, because the EVO package removed the mass and inertia, but it just acts like one electron. So you only have to put the energy in to move one electron, which means you can accelerate it extremely fast, even in low voltages, relatively. But the amount of momentum that's captured when the EVO package kind of like goes back into white mode and hits something, or gets excited when it goes and touches, for instance, a metal and gets excited by the electrons on the metal surface and impacts it. So this is what he was describing, and I have the paper, but I want to go back to the image that is the image of the this particular presentation cover slide first. So let me just get that for you. Okay, so this is the video that I'm talking about. That is the video clip that I produced the title frame from. Now, it's important that you see here that we have a normal kind of kinetic looking particle. And it comes from actually a similar sort of area on this bright intense spot when you see the whole video. And like I say, I will section these out and then group them together and have them in slow-mo so that you can actually review them at your leisure. But you see, that's more of a kinetic thing. This other one, this spiral here, is produced and goes up. Now, there's a couple interesting things that happen here. As it goes, what you don't realize is the exposure on the camera is dialed way, way, way down. It's a very short, it's 1/60th of a second, but the iris has changed such that it's letting in very little light. And this allows us to see the detail inside the plasma. So if you expose this at a higher exposure level, then you would actually see this whole area would just be one big bright glow. But because of what the camera's doing is it's trying to see detail, and it's doing its best to minimize the amount of light getting in, but still keep the shutter at 1/60th of a second. You are able to see this coming out here. Now, why I'm saying that is that this structure is moving through this, relatively speaking, densely excited plasma area. So it's born in this crack where the overexcited area is, and that leads to its production. And then it comes out, and as it goes, you see this boundary up here. As it goes through this boundary, it starts to fade, and then it's even you can imagine that it should be at least this long because it's coming towards the camera. Down here, it looks like it's at a higher frequency. I don't believe it's at a higher frequency. It's just in the distance, it's perspective. And it comes up and it looks like it's the picture changing, but it's not. It's just, it's like it's moving at a consistent velocity and that the picture's the same. But in this next frame, you'll see you're only seeing half of it. And I believe that that is because it's coming out of this dense plasma area. But the structure is still there. The structure is still there. Now, when Shoulders said you have one of these structures and it hits a piece of metal, it gets excited. You've got the electrons all over this, say, piece of aluminium, the fourth most conductive element, and it's a low melting point, which means the electrons are quite able to give themselves over to falling apart from not holding the lattice together very well. So it's getting excited as it goes into that metal. I'm saying that this may be actually a fairly neutral body even at its birth, and that it's basically being excited by the plasma in that sort of field glow area between the cathode and the anode, where you've got the bright spot on the anode up here and the bright spot on the cathode down here. And that as it passes through that area of dense excitement, it then basically loses its glow. If it was glowing itself, all by itself, without interacting with the plasma, I would imagine that it's getting closer to the camera, and it would be more intense as it goes up in terms of contrast between it and the background. So I think is it like it's a solid thing and it's reflecting the light? I mean, Shoulders did talk about solid densities of electrons. Is it so solid that it's all, or whatever it is, that it's literally like a metal spring being flung out here, and the light coming from up here is reflecting off it, and the light coming from down here is reflecting off it, and as it goes out, it doesn't have any light to reflect, it goes off. But is this actually a neutral body? Is it a neutral body that we're actually seeing? And the interesting thing is, if it is highly charged, why wouldn't it be going, and it's coming from the cathode, why wouldn't it be going straight for the anode? It's not going, this is the anode, the whole chamber is cathode, right? So why is it coming from the cathode and completely doesn't care about the anode whatsoever? Something is going on here, and I think it's extremely interesting, this little video here. But I want you to consider the shape here, and I'll go back to my ugly mug and I'll try and get the overall shape image up first. Okay. Okay, we got it here. Like I say, if I had more time, I'd have made a shorter presentation. Okay. But I think it's I want you to get your creative juices flowing thinking on this. Okay, let's go back there. So here you see it. Okay. And that is the combined shot. Here we have the, maybe I can get both of these on the frame at the same time. That would be nice, wouldn't it? Maybe we can do that. Yeah, that would be nice. So no, not there. Okay. No, we can do this. And we can push that over there. Okay, right. So maybe if I put that over there, we can do it like, no, we can't. Okay, right. You can see the whole frame on the left. Okay, and we go here, and I can just step through that. So you can see how this is forming here. Okay, now I want you to look at this and hold this shape in mind, because I'm going to show you something, and I have to dig it out first. But I'm going to show you something. So, vote for the most disjointed presentation Bob's ever done, with special Barry White audio. Okay, so I want this one, and I want okay. Okay. View actual size. Okay. So this is a presentation by Ken Shoulders, and yes, it's not a sinus problem, David. This is a presentation by Ken Shoulders, and it is called Evo Propulsion Basis. And he's looking at this aluminium sheet that he has here, and you have these incoming Evo strikes, and they go boom. And you can see some of these that might look a little bit spirally, but let's not focus on that. And some of them have what he calls reversed Evo regions, and this is where the Evo doesn't quite make it through the aluminium foil, and it blows out the backside. The same way it came in, but it blows out the backside the same way it came in, with all of the matter that it's captured from aluminium that it's passed through. In the case over here, you've got material that is being thrown out the back here, okay? And what he is suggesting is that you are able to accelerate these things as if they're a single electron, and they are able to capture material as if they're not really there, and you have a mass rectification process going on, and this enables propulsion both forwards and backwards. And he's also got these what look a bit like our spiraling streaks coming through as well in different and a different one here. But here is this image, and what he's showing you here is ones where you have a hole. This is where it is punching straight through, and this is what he calls forward propulsion. And that is these ones here with the jet coming out. And the ones where you've just got the dimple here, these ones over here and here, these are what he calls the reverse propulsion here, where it is capturing some material but not making it all the way through the aluminium and then throwing the mass back in the opposite direction. Now, it's the next frame that I'm most interested in. And I'm going to give you a few seconds to guess why. It's a close-up of this area of this particular Evo exposed aluminium foil. Aluminum for you Americans there. And he's got some notes on there. He says, large explosive eruption due to the high momentum transfer between the exotic vacuum object and coating material. Normal 20 micrometer Evo passage through a coating and aluminium foil. Note offset angle here. What am I asking you to see in this frame? What am I asking you to see? First to get it. Who's first to get it? Ta-da! Well done, David! You get the prize! And Ken Shoulders never mentioned it. He never mentioned it. Now, the very interesting thing here is that under the scanning electron microscope, you can see this white edge around where the Evo punched through. Over here, you see this Evo punched through and the white edge. And this is something that seems to be quite telltale. Now, what has David just pointed out? He's just pointed out what I'm going to show you here, and I've blown it up, is this. This. And what did I ask you to hold in mind? Dave, you deserve it because this is your track. So, have we, in this particular presentation, I have shown you tracks that change direction completely. We observe this in strange radiation tracks. I've also shown you tracks that look like an M. They've got a curved part with a bottom and a curved part and a bottom, and then they have a spot in between. A spot in between. I will also show you in another presentation, because we're past curfew here now, ones where you have rings, and the rings are moving around in random directions. But anyway, what you are seeing on the screen right now is, for me, an almost one-for-one, where you have a video of the motion. And as I've described it, what you're looking at here is something that could be neutral. But if it got through and for whatever reason happened to travel along the aluminium in this one, it's actually got excited by the electrons in there. And what am I saying? I'm saying that an EVO can be in a white mode and a black mode. In a black mode, it can go through materials. So, for instance, EVOs are known to go through glass, for instance. It can go through glass but leave a hole, and sometimes it can go through glass and just leave a round ring taken out. Okay? So, is that because it got stuck in place and got excited and then just popped out? And there's a Russian researcher that actually simulated that and actually has the piece with the round bit cut out. Okay? So if it's in its unexcited mode, which I believe quite possibly that this is a neutral EVO, but it's so dense that it's kind of either capturing light or reflecting light, or there is some interaction between either the photons or the plasma, the ions or the electrons in this matter here, but it isn't attracted to the anode and it's coming from the cathode. It implies to me that this is neutral. If it is neutral, then it can come out of the reactor, and it can come out of the reactor and subsequently be excited for whatever reason. Just as the situation was right for it, it'd gone through enough material so it got into a state where it was going to be excited, it would move on. So we've seen things going in different directions, things that have straight lines and then go into squiggly lines. We have double squiggly lines, single squiggly lines. And you can see that if this spiral here was 50% of the way through a material, it would create little spots 50% apart, on either side of it, as it's corkscrewed through a sheet of material. Or if it was a double helix, you would get, again, a different one. Now, there are these things that are folded in on themselves as a torus, and they produce a different track. And then there are those that then are clustered into much larger structures that then can roll about, as Bogdanovich has showed and as was observed from a plasma glow spark plug that we put on the Steamer channel in 2017. So, is it creating its own motion? Have we got two structures that are moving around their combined center of mass? Is it have its own forward intense magnetic moment, and it's kind of like following its own magnetic beam? Is it just a single thing and is it just going from side to side? Now, I am going to call it a day, but I'm going to show you other paired videos where you can see in one video that it just looks like it's a straight line. In fact, I'll see if I can find it now. But in one of the paired videos, you can see it's a straight line. In the other video, you can see it's a squiggle. So sometimes it literally is moving from side to side, okay? Sometimes it's clearly going in a spiral, as I believe that I've fully demonstrated today. And I have hopefully also shown you that they can interact with each other and cause the changing direction. And if we didn't show that with the large piece of tungsten that had a 50% of the way round on the coil, on the anode, in Dave's experiment, you had another plasmoid build up, another ball lightning coherent matter structure, and it cut the tungsten. And as it fell away, if you remember, it aligned the magnetic poles, in my understanding. It's so powerful, but I think it's very, very focused. It's very, very focused. The beam that comes out of these structures, it's like an intense magnetic beam. It's not a normal kind of magnet structure in terms of that kind of thing. So again, these structures here, which are multiple frames joined together, but the key things are, again, this is an artifact here, and this is where it goes up and it kind of squiggles around a bit and changes direction, almost looks like it changes frequency. And this is the sort of thing that you saw in the ball lightning in Hessdalen light. So if you go to the Steam It channel, I did a whole series about Hessdalen ball lightning, and the videos are on MFMP's YouTube channel. And you can see when the ball lightning hit the top of a tree, it then went into a spiral, and then it hit another tree and went into a broader spiral. So they can get disrupted, and all the time they're moving in the same medium. They basically don't care about anything. Now, I want to go to another shoulders presentation, because I think it's very relevant to what we've just been discussing. So let me find that for you. And I will, of course, share all of the links in the remoteview.icu that I'm referring to here. Okay, I'll just finish off on this particular presentation. So he's saying that these are the splatters. So this would be the forward motion, and these are the no splatter. This would be the reverse motion. And he describes it here. The sequence of EVO propulsion events. Forward motion. An EVO is launched from the electrode of a pulsed high voltage source. The EVO travels through atmospheric pressure air and strikes the surface of a cured mixture of silicon carbide and epoxy cement spread on an aluminium foil. The EVO bores through the mixture layer as well as the aluminium foil, producing a clean 20 micrometer diameter borehole on the way in. Some holes are bored just short of the aluminium foil, and others bore completely through with excessive energy, largely due to the variation in silicon carbide layer thickness. Excessive energy holes expel fluidized silicon carbide at a high velocity in the forward direction. In the reverse motion, for a large percentage of holes, EVOs bore completely through the silicon carbide and aluminium foil, and then reverses its direction, likely due to an open circuit electrical impedance mismatch. This reverse motion of the EVO carries with it all material it has disrupted to atomic form and propels it towards the top side of the silicon carbide mix. The material is ejected with high velocity in a reverse direction to the entry direction of the EVO. A strong emission of light from a point source is recorded on the film, confirming the fact that the penetration of the aluminium foil and charge acceleration had occurred. Not a trace of ejected material is found below the hole on the photographic film recording the operation, indicating no rocket-like action had occurred. Conclusion. A heretofore undocumented form of very powerful and efficient propulsion is displayed, indicating a connection has been made to something outside our usual sensory system. So he actually has another paper on this, so I will try and get that for you, because it's relevant to specifically what we are discussing here. Now, you can go and find these papers on Rex Research, and the guy that runs Rex Research, thank you very, very much for all of his work over the years to put that together. So, this is called Mass Rectification as Propulsion, or Knowing When It's Time to Leave Frontier Science to Someone Else by Ken Shoulders in 2008. So he has some criticism here about the standard way of doing science and his way of doing science. And he's saying, like, publish nothing until it's finished, as only a finished invention speaks effectively. Yeah, well, I think probably this presentation might fall into that category of it might not speak effectively, but I hope that I've shared enough of these beautiful images that are coming out of the Vega experiments to convince you that possibly what is being produced is really very interesting. It is what Ken Shoulders has already shown us before, but at higher fidelity and in videos that you will be able to examine in your own time. Okay, EVOs allow violation of mass, momentum, and energy conservation laws of conservative single particle physics. I like the way he plays that. He says energy conservation laws of conservation, but he actually says energy conservation laws of conservative single particle physics. New multi-particle EVO physics laws readily allow such conservation violations. So he again draws on this image here, early indications of inertial propulsion possibilities. And so this is from Charge Clusters in Action, and I've already explained this in the previous video. View of EVOs carrying massive loads of atoms is partial testimony to mass reduction mode. The assumed limitations are no ion loss going into sample, but much coming out both ways gives EVO carrying limit. Long path length going in is to give clearance for reverse ejection and is not fundamental. So yeah, so he's saying that you don't need to have a path this long, but he's got it this long so that there's a significant clearance between the reverse injection. Now, this is a negative of some images that he captured rather in September 1983. September 1983. And he has a whole sequence of these, switching over EVO between white and black state and internal EVO energy. I don't know whether he has it in this one. Field-induced black to white transition. Okay, it wasn't this one, but okay. So you could do mass rectification. Let me find. There's another video, another presentation that he does, which demonstrates this neutral aspect that I was talking about earlier. So let me find that. And it's actually in his book, Evo Tale of Discovery. He refers to it several times, and I don't blame him because it is really an astounding observation, and it is a real shame that, or actually quite exciting actually, that it's taken volunteers working with a volunteer organisation funded by the crowd to actually replicate Ken Shoulders' work to this level. I mean, it might have been done in other labs that have actual funding of very significant nature, but in terms of the public space, it's taken volunteers' initiative and the crowd to just actually get this done. And I really believe that if we're going to benefit from this technology, let's not wait for anyone else to do it. Let's not wait for some announcement of something that they discovered in the 1950s and 60s. Thank you. Let's just get on with it. We can do it. Okay. Let me see if I can find this. Yeah. Okay. Okay, I've actually got some notes, so maybe I'll look at my notes on it. Okay, let me look at my notes because I've got some notes. Talk amongst yourselves. Okay. Maybe I can find it like that. Okay. Right, here we go. This will do. Okay. Okay. Are you still invested? Right. In order to develop some reality about the appearance of white and black EVs, this is what he was calling it in EVs, A Tale of Discovery. He then later called them exotic vacuum objects. Refer to figure 5 and 6, which I've got in shot here, with each showing a single run of an exotic vacuum object towards a target at the top of the photo. These photos were taken from 1, as figure 4.4 and fig 4.42, where there is other photos showing similar effects. What can be seen is the white EV, exotic vacuum object, coming in from the lower side of the photo and then disappearing from camera view just before striking the target and disintegrating it here. So down here in the bottom, and the bottom here of this other shot, you have the white EV, and it kind of disappears at this point before it strikes a target up here. Comes up, disappears, and strikes a target. Okay? Before striking the target and disintegrating it. The white glob at the top is a plume of ions coming from the explosion. This can be validated by applying an analyzing field in the camera that produces a deflection of the ion to the left for ions and to the right for electrons. So I would imagine that there's an anode on the right-hand side of this right-hand picture and a cathode on the left. And so the ions are being pulled over to the left, and the electrons are being pulled over to the right. And he says here, deflected ion pattern and deflected EV run. Okay, so the analysis field has been applied in figure 6. And it can be seen that the white EV, exotic vacuum object, has moved to the right, signifying its emission products are electrons, while the ion plume moves to the left. The fact is, there is an omission of both electronic and optical traces during the black phase of the EV run. This is not an artifact of the measurement method, because there are many examples where multiple cameras and visual observations showed such disappearance in the black state. There is no ability to ionize gas or to excite fluorescence from nearby dielectric materials where there is with a white EV. So he's suggesting that you actually have the plume up here and the electrons going over here, but the path of the EV is essentially going in the same direction. This is some of his sort of approach to confirming the neutral nature that EVs can have. As an aside, the question of fractional electronic charges becomes moot under the conditions discussed here. Although there are too many electrons in the process to determine a single electron level for a quantum check, it appears that there are many states of charge expression as the transition from white to black is made. Some of these could be like fractional charges in appearance. There are no obvious consequences of this effect. Under the conditions, that's basically this particular paper I'll link in, and I'll do some further discussion on it because I think it relates back to what we have been discussing in these videos and so forth. So where are we? This one, not that one. This one. So I think probably that's all I want to say tonight. It's Martin Fleischmann's birthday tomorrow, and I have something special that I want to talk about. I've been working with a guy here in Prague on it, and it will be probably for next year, and I want the community to potentially consider it. Obviously this week is also the week of the 32nd remembrance, or whatever you might like to call it, of the event that took place when cold fusion was announced. But I think that the work of volunteers for the project, and particularly the work of Russians over the years in getting to the bottom of strange radiation is really something that we are possibly getting closer to finding an explanation of. I actually have a presentation here by, actually there's some material by Arutkev which is worth just dropping in here because of these traces. And it's in Ken Scholder's work, actually. He's referring to different EVs and so forth. I'll actually bring this up here. So it's this one. Is that going to do what I want it to do? So you've got some Arutkev, Leonid Arutkev imagery up here, and you can see this is the dual EVO as imaged by Ken Shoulders, and you can see it's breaking up the top here, and this is a kind of track. It's not finely resolved here. It kind of like has a straight line and two dots, straight line, two dots, straight line, two dots. This, for me, is kind of one that would be a dual EVO, where there are slightly different properties between the pair. This is potentially a dual track, and you're seeing the diameter of the track here as it's going through the material and so forth. But I have some other work by, I go here, by another author, who you could probably go and investigate because he's done a lot of work in this area, and his name is it slipped my mind just now. Okay. Okay. This is a track accredited to a paper by Zhigalov, and it's in a presentation by Ed Lewis. He's credited Zhigalov with this, but I actually recognize this from Solin's 2001 patent, and you can see that potentially we could say it's a similar track to this observed by Ken Shoulders, and it's a similar kind of structure to that which you are seeing here in the video of Dave in the Vega experiment. This is one that's more like a standard type of helix. This is in Baranov. Baranov works with Zatelepin in Russia, and you can see the spiral here. And so these things are, I think, getting to the point of being demystified now. So I'm going to ask some questions if anyone's got any questions. Otherwise, I'll call it a night. Okay, so time to ask me some questions. Is a triple EVO possible? I don't think so. When I say that, you can get clusters, and they form bead chains, but the actual beads themselves, I believe, are actual superstructures themselves, and I will do that when I'm arguing what I believe is going on with this puppy here. And the anode I showed you earlier in the Dave experiment, where you can see when I've merged all these layers together, you can actually see these bright spots and the channels that are less bright leading to them. And in fact, I think I'm going to give you a real treat right now. I'm going to give you an image that's going to illustrate that. And it is here. Let me find it. Is it here? Yes. Is it here? Yes. Here. This is a stack shot, and I'm working on improving the stack shot. So you can see, and when this will be very useful when we look at the SEM imagery, because we've got fragments that are probably from this area here, this kind of black charred area, and this is in the central valley, as I call it, this central valley. And then these are the kind of tributaries, and it's in these tributaries where you get these round spheres here that like tend to stop. And so what I'm saying is that what I showed you earlier on the anode is the feeder lines, and then they get to an endpoint. The endpoint becomes very intense, and that is the bright spot that you see. But it can persist even with just less being fed to it. I imagine that this is a bright spot that didn't spend very long time in this location, and maybe it's the same over here. But these, for instance, were there for a much longer period of time in this channel here. And these structures here, I hope to be able to fully explain in my up-and-coming presentation with the scanning electron microscopy, which I received yesterday and this morning, and with the hypothesis that I have beyond why this is so phenomenally ordered. So yeah. So I don't believe you get 3. And to clarify that, if you remember I think it's called Tungsten Chop Shop, or the video where I was describing how I believe that it was the one that was really seminal for me in showing that these were magnetic structures, that they were coherent structures, and that it was only the thin layer on the boundary that is doing most of the work in cutting and so forth. So when you have that coil that on the anode and that Dave Vega experiment, and it comes round and it burns round, and then it gets to a certain point, and then over here another one builds up and another one builds up until it gets to a certain strength, and it suddenly cuts the tungsten, it falls away. You get this magnetic alignment, and I think we know that the structures they like to form certain structures, but it's either one on its own. So the bit of tungsten that went away, it went with one, and the other one had another one that formed on the other side. So there's like a pair, and if that pair was formed in some location without, it's kind of like it almost needs its own. In that sense, you're making a very large structure on which it to form, but you might think of it like that, doing that on its own in a cavity. I don't know. I'm just hypothesizing here, but what is observed is that you see 2, but I believe these things are massive clusters. Those ball lightning, it's actually many, many clusters. And if you refer back to the previous video where we were discussing these Vega experiments and the traces, we had I mentioned it earlier, we had the big plasma ball, and then we had what I said was it appeared like a kink instability. And I said this at the beginning. To me, that implies that you have a magnetic flux loop, which would imply that you have a north on one end and a south on one end on this coherent matter structure, which means for me that the actual overall structure is made up of very much smaller magnetic domains, and these can then maybe separate or split, or when there's an instability, you then get this ejection of magnetic flux as it kind of folds out, just like you see on the sun. I mean, from my view, we really are working with the same stuff, just on a smaller level, and all of the principles apply. And it's just normally astrologers, astronomers rather, and physicists, they look at the sun, or they look at some other heavenly body, and they try and work out the maths to explain what they're seeing on their big telescope or their big satellite or whatever with the nice lens. Where I think what we're doing in the Vega experiment is actually doing the same thing, but you can actually see it. And what's been incredible since this was first observed by Henk, the spiraling kind of, or the at least side-to-side translational motion, since that was observed, within days, Dave had replicated it, and it's been replicated multiple times, and with rather simple equipment actually. And so this is science. It's science. It can be done every day of the week. It would seem that the crack might be important to enhancing this phenomena. And you might like to think that if you wanted to create very much smaller ball lightning, for instance, in a Lena experiment, that you might want to have a crack or a surface feature, like a promontory, a prominence, a spike, or whatever, that was at a different resonance scale for however the energy is being fed to the material. But Ken Shoulders showed us that we can create coherence, in my view, with discharges. I think John Hutchison showed us that we can create it at room temperature, and the Lockheed Martin patent, coherent matter waves, that shows you that it's not actually important what the temperature is. It could be like making a Bose-Einstein condensate at absolute zero, because then all of your atoms of the same type, like sodium-23, for instance, or aluminium-27, or fluorine-19, they're all at the same temperature, and that means that their Broglie wavelength is the same. All you then need to do is get it in phase, and that's the whole basis behind the Lockheed Martin patent, is it doesn't actually matter what the temperature is. You just need everything to be the same atom or the same thing, like an electron or a proton, which is nucleus of hydrogen, atomic hydrogen. You need it at the same temperature, so it has the same Broglie wavelength, and then you need it in phase. And if you go to the Serlin patent, if you go to the work of Matsumoto in his proposals in the 90s and so forth, they are saying that you just need to create electron bunching. And I believe that the ball lightning self-organizing structures on this boundary layer, this very fine layer, you have electrons coming in and a pressure out. And so you naturally have electron bunching. And so it's kind of like they all have to settle to be best arranged in an electronic speed. They have to be settled so that they're all at the same temperature, whatever that temperature is, whether it's a Hutchison temperature at room temperature, or it's a plasma temperature in the Vega experiment. It just needs to be at the same temperature. And because they're effectively held on this elastic membrane that has a force out and a pressure in, they effectively are like a load of metronomes that are out of sync, and they get into sync. And so you then end up with this whole coherent structure. And the coherent structure likes to be that coherent structure. Now, you can have an instability, and a part of that substructure can maybe blow off, and maybe that is what strange radiation is. It's just an on-off event or a random event, or the whole thing blows up and parts of it are still intact, as it appears we've observed in our experiments with Echo Fuel in 2017, and it would appear that Matsumoto has observed with these star formations, and we may have even observed it on video in the last presentation that I gave using the Vega videos. You have this like boson over, but some of the fragments of the original coherent body come out, and they are still the same temperature and the same phase, and so they're still coherent. And some of those might be in pairs, and they might then be forming the strange radiation, which might go into black mode and then travel through material. Then, for whatever reason, they get excited, having gone through a certain amount of material, and then they go into white mode, in which case they start to interact with material. And it's like that ball lightning where the material inside isn't boiled or sintered, like the water isn't boiled or the sand isn't sintered, but if the ball lightning goes into water, it will boil the water. Okay, so it's stuff coming from the outside. So as your strange radiation is coming and it's hitting the metal surface and it's spinning around, okay, it's excited, and it almost doesn't see the material. It's like it's able to disrupt and grab those electrons, because it doesn't, the neutron, the nucleus almost isn't there, and so it's because, like, you know, most of an atom is its scale is actually the orbits of the electrons rather than the actual scale of the nucleus. And so from its point of view, it just doesn't see it. It likes to interact with electrons. And so the remaining ions get swept up because there's a newly negative thing in its field of influence, and the ions get carried along with it and they become part of it. And so it kind of feeds itself. As it condenses that material down, it yields energy, which keeps itself excited. But because the whole thing is on this springy membrane, it keeps itself coherent even as it gets excited. And so, I don't know, I'm throwing some of many ideas and concepts that I need to spell out in much more detailed presentations. So that was a long answer to a question. Okay, so did we have a question too? Okay. Whoa, I don't even know where the last question was. I don't even know what the last question was. Okay. Okay, I can see. Please get yourself out there as a guest on high traffic podcasts and live streams, even if you think it's unnecessary. The world needs this knowledge. Thank you, Join the Technicians. Yes, I think they do. You've got some great stuff on your site, by the way. Yeah, they definitely do. But I think what's happening right now is, in the last video, I did say that if there are people that are willing to say on video that they're willing to accept the risk and sign a document to say they're willing to accept the risk, whilst there are circuits similar to those that are being used in the Vega experiments out there and they're already being documented, we're not wanting to get into the litigation business, and this does deal with voltages and systems that can easily kill people. So it needs to be something that competent people can do or choose to do of their own volition. And our focus would just be to advise them on safety, but they should be prepared to know the kind of safety precautions they need to take when dealing with high voltages and gases, which could be explosive. Okay, thank you for the offer of help. Yeah, I mean, what I've talked about, I've talked about Ken Shoulders. So if you look at the 2010 interview that I transcribed between Ken Shoulders and John Hutchison, and John Hutchison's wife, and that's the transcript is on Steemit. When you look at that interview, he's talking about, oh, you know, you're doing anti-gravity, and he says, I'm not really bothered about anti-gravity. Give me propulsion any day. Basically, anti-gravity is only useful where you've got gravity, but propulsion is useful everywhere. And I have described the method that Ken Shoulders has described for propulsion. I believe that what I've already shared in the last few years, with some other stuff that I'm working through, and I've shared actually the things which are important, but it's not obvious. So for instance, even Ken Shoulders missed the fact that he had a clear Evo mark on here, even when he was discussing about his work producing the same thing as Reutzkev. He had already observed it. So you can even miss things, and you need to go back and look at things in the light of new information that comes in, because you literally do forget things. And so, but I haven't forgotten this, and it is about another form of way that these structures can be used and manipulated, I believe, to do propulsion, which would appear as anti-gravity, but it's actually propulsion, Okay, so the ball itself can produce a negation of the effect of whatever gravity is, but it's still not moving you around. It's the propulsion thing that you need, and it's better if it's at least propulsion to move you out in space. And I believe exotic vacuum objects are able to do this in a very different way to one that's described by mass rectification. That, as described in what I've said today with the evidence that I presented in video. And so I will talk about that, and I believe that this is already known. It's already known, and they're running out of time to make it public. Let's put it that way. How would you combine EVOs and Leif-Homlid's ultra high density deuterium? In my view, they are EVOs can make ultra dense anything, and because deuterons or protons are the same nuclei, they can be made coherent and smaller, easier, because you've not got multiple isotopes which would have a different de Broglie wavelength and interfere with each other. Deuterium, additionally, is a boson, so unlike the protons, which can't occupy the same space-time, the deuterons can, and so, in my view, they can be condensed into dense matter using exotic vacuum objects more readily. What level of vacuum is required for stable exotic vacuum objects? Stable exotic vacuum objects exist as ball lightning. Therefore, you can do it without a vacuum. You can do it with a vacuum. In case of Ken Shoulders, he said that heavy ions are good for stabilizing exotic vacuum objects. So if you go to the, I think it's 1930, 35, 34 description of Tesla's death ray, that is, he's got a dry steam jet that creates an open-ended vacuum tube, and then he feeds either tungsten electrode wire in or mercury in. So he's got a liquid electrode which forms a Taylor cone, and then he uses the discharge out from that, and he says that it produces electrical particles of matter in a separate newspaper article. So I think he had a good understanding of what was going on, but of course he didn't have fast cameras and stuff and couldn't see it from that point of view, but he could see that he could fire at extremely high momentum minute electrical particles of matter. So in that case, he's creating a vacuum, but then it goes straight into a atmosphere through dry steam. And the dry steam actually might help stabilize it. It is a gas in itself, and it has oxygen in it. I've discussed how oxygen, and I will discuss in detail how I believe that can play a major role in water-based technologies that essentially use this same phenomena. So if you use xenon, I think one of his choices was xenon because it's a very heavy gas, and so it's kind of like you can carry a lot of mass, but it stabilizes. Basically, the EVO is at its basic structure, according to Shoulders, a torus, and according to Matsumoto, it's either a torus or a sphere. And I would agree with that. It might be that the sphere is made of clusters of toruses, and that's not too far from the observations of Bogdanovich. And so, from a distance, it looks like a sphere, but if you can look at it in more detail, you then start to see it has a crystal-like substructure. And we've observed this kind of crystal-like substructure on webcam. We've observed it on the Amata vibrator plates, and those are of the same scale and same morphology, it would appear, to those that were observed in one-point explosive cold fusion in the 1990s by Takaaki Matsumoto. Do double EVOs behave like neutrinos because and I know it's not proven, but neutrinos being its own antiparticle are EVOs. Imagine this, and this is something that I wanted to share for years, but it's in a little nutshell. Alexander Parkhomov in Space, Earth, Human goes through the decades of proof that he went through to establish that relic neutrinos, or N radiation clusters of, can be reflected, so therefore they are large wavelength, and he was looking at ones that he determined through diffraction gratings were in microns to millimeters, and he then focused these onto, for instance, cobalt-60, which has a 5.1 year half-life or something. It's a beta isotope, and it decayed with stimulated decays because of the beta energy coming off was at the limit. Therefore, he knows it's because of stimulated decays and not natural decays, and he screened for that. He describes exactly how the whole process is done and how you screen for it in his book, Space, Earth, Human. And this then says that it must be acting as if it is a neutrino, and therefore is likely to be called neutrinos. The Russians at Dubna since 2009 have been studying these things. They call them magnetotoroelectrical radiation, and they say at least the neutral form that they get out of, for instance, a cavitator, or from a gamma source, or from a range of different methods like a spark discharge, a range of different methods to produce these things, they act as if they are condensed torus of cold neutrinos, and so that is they call it magnetotoroelectrical radiation, but they give credit to Shoulders, as is rightly the case. Now, that isn't to just say that they are neutrinos, because they have observed them carrying a payload of ions, whatever material that they've travelled through, and this is what I've described in the papers that Shoulders has said today. They basically atomize the material, atomize it, and they entrain that material with them, and so they can carry that. And when they disrupt, they actually characterized, Shishkin did, and you can go and look at that. I think the presentation's something like a new form of penetrating radiation by Alexander Shishkin. It's from his Sochi 2018 presentation. They characterize the depth and the width of the pits of the atoms that are carried are relative to the atom. So you have a heavier atom, it makes a bigger dent, and therefore if you're going to maximize the rectification of mass propulsion technology that Shoulders was describing, you would want to be using xenon, for instance, as your atom that you are carrying with you, and making your EVOs from, and losing the mass, but being able to accelerate it and gaining that momentum for free. And so, so it was, so basically, they can act like neutrinos, and an electron can share its energy with neutrino, because the weak force is something that's enabled, or there's neutrinos involved. You've got bosons, but anyway, W bosons or whatever. But you have you can have an equation where you have an electron and a neutrino, and an electron and a neutrino on either side of the equation, but they can exchange their kinetic energy. So, for instance, if you have a highly neutral thing, and you have a large amount of electrons at a high density, they can maybe exchange the energy between the neutrinos and the electrons, and vice versa. And when Parkhomov in his book describes how you technologically produce, and in his papers, cold neutrinos that are equivalent to that which was produced in the Big Bang, called relic neutrinos, when you have this condensation of matter, the temperature goes up on this boundary layer, as we know, or it would so appear. And if the temperature goes above 1,000 degrees, then it starts to produce cold neutrinos. And so the actual condensation on the boundary of the self-organized plasma structures, that is where you're forming these cold neutrinos. And then the cold neutrinos are then forced to self-organize. And so you can see how one follows the other. Yeah, David not using high vacuum in his experiments. Join the technicians. I don't think you're an idiot. My view on the Marty Fleischmann Memorial Project's YouTube channel is I kind of been happy to be in a small audience because uh, I said in the beginning of 2017 when all of this is done, there isn't a person that's going to have, there almost isn't an industry that isn't going to have a problem with what this implies. So you kind of want to get it out. uh, uh, David, uh, I'm working on the John Hutchison the book, and so you will hear more about that in the coming weeks and months. Things are moving ahead. Yeah, it's quite possible that I think in the lion experiment I described, like for instance, shoulders. We know we had bead chains in lion because we saw them on the outside of quartz, and the bead chains tend to move as a group, and it may be that they are born out of the same initiation point, and they are essentially entangled. And I think in my Sochi presentation, I described it like you can imagine like a bead chain, and I had my hand like this, and I said like it scratches its way around the surface or it eats its way in a direction. So, but I'm not necessarily saying that every single one is the exact same thing, but in different locations. But it could well be that. I mean, diamond is. Uh, uh, One of the strongest materials there are. Like, okay, and so if there was any, it's very stiff, is what I'm saying. So there's a good chance for any vibrations, whatever they are, to be homogenized across the surface. So you could have a state where everything is of the same wavelength and maybe all in phase, and so they're kind of like coherent in that sense, just because they were born on a diamond. Uh, um, Not because they were necessarily nucleated from the cell at the same point. Yeah, Shoulders changed his opinion of what exotic vacuum objects were over his experience with them. He first started off by calling them EVs, then charge clusters, high density charge clusters, and eventually called them exotic vacuum objects. And as I said, is it the vacuum inside that's exotic, or is it EV as in E actually meaning electron and V meaning neutrino, i.e. electron neutrino object? You know, you can look at it, but I'm not going to speak for him. But um, Matsumoto came from a different direction, and he from the outset, very early on, I think in 1991, said that uh, these form mesh-like structures or rings or spheres, and that they are combinations of positrons, electrons, and neutrinos. That's the mesh, and then the ions are captured in there, and they can be vast numbers of ions. And given the condensation process, and that you will produce cold neutrinos when you have high temperature, highly dense material interacting, it's not unreasonable to suggest that Matsumoto was right. And certainly the observations by many parties of neutrino-like stimulation of beta isotopes transitioning. There's almost nothing you can, there's basically no other way you can describe it. There is something that is doing exactly what a neutrino would do, and you know this, and it's extremely and explicitly with all the experimental data, all of the calculations, and everything you need without anything omitted in the book by Alexander Parkhomov, Space Earth Human. Yes, there will be many links. What I tend to do is I'll go through video and I'll listen to things that I've referenced, and I will, the papers that I've shown, or shoulders or whatever, I will give a link to them. But the ones that I showed of shoulders here are available on Rex Research. So if you actually look at the title slides on those and then type that in and say Rex Research, you'll find it. What we have seen in our experiments, and Matsumoto observed because he had things going through his experimental apparatus, so did Ed Storms, and obviously so did Shoulders, so did John Hutchison, many different authors, Roitskev, Shishkin, all his team, they have all observed this phenomena of something that has to have been neutral at some point, and that can switch between being neutral and charged. And Shoulders describes that you can have 100 billion electron charges, and then it can go all the way down to 1. He says I can vary the charge of these things 100 billion to 1 easily every day of the week. And so what he's describing is something that you can manipulate the charge, and you're not changing the mass. And so is it a reorganization of the matter, so like everything's becoming like a neutron in there, or is it that they are organizing in a coherent way, so you're effectively ending up as one large electron? Now, he specifically describes in that presentation, that interview, he says, you know, a muon an electron has a charge of -1, a Cooper pair, a muon, a tauon, these all have a charge of -1, with the Cooper pair effectively being a pair, and it's actually a boson. And so you have a range of different things where, you know, I need to check on the charge on the Cooper pair, but anyway, certainly on the muon and the tauon. But a muon's like, whatever it is, 207 times the mass of an electron, and God, I'll probably get this wrong, and you can check it because you can. 6,000 or 6,700 or 5,700. It's many thousands of the mass of an electron, but it still has a charge of -1. And what he's saying is you end up with a structure that acts as if it is just a very, very large lepton, charged lepton in this family. And you can imagine that I guess if you could fit matter inside an electron, one electron or a muon or a tauon, then that matter would lose its mass. I don't know, but essentially I'm saying that these structures are coherent, and they express themselves as a unitary body where it loses its individual identity and becomes a thing where the whole thing expresses that single charge. Well, Hawking, as he got into his later years, this isn't a question, could strange radiation be an interaction between Hawking radiation and Unruh radiation? So Mike, is it Mike? The guy at Southampton University, anyway, talking about Unruh radiation as a means of propulsion. And Hawking kind of like, I think I'm right in saying he kind of semi-walked back the idea of the black holes event horizon in the way that he originally described it. Anyway, I'm not an expert on that. What I do know is there appears to be event horizons around exotic vacuum objects. and that they uh, uh, are able to reorganize matter into a way, into a state that is a new phase of matter. It isn't, well, not new, it's ubiquitous, but it's new in that lots of scientists don't consider it, and it's not in your textbooks generally. This isn't solid, liquid, plasma, gas. You know, it's another phase of matter. Uh, I'm not so sure. Axel, you're saying EVOs produce energy by converting nothing into positive and negative energy. Um, I will describe an experiment that was done by Shishkin separately because it relates to this other form of propulsion, and it's a very large topic. But this observation is key, and it's about getting energy at any point in the universe. And I'm not talking about zero point energy. I'm talking about the thing that we have observed in our experiments and has been observed by many parties, just applied on a different subquanta of available resources that are available at any point in the universe. So you don't need to create something out of nothing. You are shifting one energy form to another. This doesn't. You might be changing mass inertia and charge laws, but you're not changing actually a conversion of one type of energy into another. And in case of the condensation in the structures, my series of blogs called "What Goes Up Must Come Down," which I have two more sections to do, by the way, on remoteview.icu. This will go into the justification for my arguments in that in coming months. But essentially, when the material is being condensed, it's releasing energy to become coherent, and it must effectively get that back. But it's kind of like it's almost like a heat pump. Let's put it like that. It's like a heat pump. And so you can use the energy, and then if the thing gets neutral and goes away, it doesn't matter. You just make another, and you kind of like you're what the Russians said in 1992, and I believe they were right in that CIA document that we shared on our Facebook page. They are releasing the hidden energy in matter, and they specifically said in that CIA document that using 1 kilo of iron, they could use a propulsion technology that got its energy from that 1 kilo of iron, the hidden energy in the 1 kilo of iron, to get to Alpha Centauri and back. And I believe that is possible with this technology in 12 years. And that's the what they quoted. So to another solar system and back within 12 years, and the energy source is the hidden energy in 1 kilo of iron, and the means of getting that energy is the same means by which you are propelling the craft. Um, I would counsel you to look at this. This is Gardy asking, are you saying that EVAs produce Hawking radiation? And if so, what Bremstarting radiation then? Um, oh God, you can go and look it up. Both of those things. One's breaking radiation when you've got a particle like electron going through a heavy ion, for instance, a heavy nuclei like tungsten, and you get photons coming out, and that some of the kinetic energy is released as a photon in breaking radiation. And Hawking radiation is the radiation that comes back when something goes into a black hole, but it's kind of like it deals with the paradox. Like some information's coming out that way, some information's going in. So it's kind of it deals with that paradox. But I don't want to get into that because I think what you can observe with what Sviatmenko shared in a 2006 interview with American Anti-Gravity. He was talking about structures that he observed on his accretion disks from his relativistic discharges at 1/10 of C, into a target, there were structures that when he fired primary ions into, primary ions disappeared, and it emitted light, and it would appear, and he didn't see any second ions. So whatever those little black blobs that he saw on his weeks or however long it was after his experiment, they were able to absorb matter and convert it into emitted light. And you can go and look at my discussion on that and the link to that in my 2018 Sochi presentation. Yeah, I think nature's wheelhouse is in our grasp. In fact, sadly to say, I think it's probably been within our grasp since 1910, since Tesla gave his Sun New York article, and I think probably I it's a shame. I think anyway, it should have been already available, but there's too much bad technology to sell first. Let's put it that way. Having said that, there are reasons not to use this technology because, it produces ionizing radiation, which can kill. It can disrupt materials, which makes it difficult for having landing and launch sites. You can turn things into jelly, like and it's not known, but we are learning about it. It produces strange radiation, which is been with us throughout our evolution, but there's a certain amount we can handle because we evolved with it in the natural environment. But if you had a lot of this, you can't handle it. And this is why people are dying of cancer that are researching in our field. We're so very keen to have certain levels of safety involved with people that are researching this, because you can't see it necessarily on your normal detector, and it's not always predictable when you will produce it. So, but if you have a device that is able to do some pretty, what would seem magical things, then it's likely that it's also capable of producing things that are undesirable. Yeah, well, you've seen Shoulders in the paper that I discussed tonight talk about how an exotic vacuum object can reduce things into their atomic state. And if you look at the presentation in ICCF 22 from 2019 by Lutzi Aitner, he describes how the torus version of an exotic vacuum object, which he calls condensed plasmoids after its original namer, Winston Bostic from the 1950s and 60s American fusion research. He says that the density of the ions in the core ring of a ring structure of a plasmoid, the ring type, can reach 5 times, I think, is the density of the sun. Same density of nucleons as you would see in a pulsar, which is a type of neutron star. So it's unsurprising that when these things self-compress and explode, you get all of the elements in the periodic table. And alchemy is possible. What you want to do is to get the state where it's coherent and the nuclei have effectively lost their identity. You want to be able to give it a template so that when it does this process of coming back into our physical reality, it has templates to crystallize onto it, for want of a better word. And I described something similar to this in my 2017 ASTI presentation. I described it in kind of like well, you can go and see it, but Axel, you know what? The energy may be coming from the Higgs field. It may be. I like to see what I can see. You know, someone else says that there's this field here, and you can look at all these beautiful equations, and we found something in the Large Hadron Collider. But all these things are kind of like ethereal. They're not something that I can observe and go, well, I know that is. I know what I'm looking at here. And I know that this is I know that this is the anode, and I know that this is the cathode, and this thing is coming out. Like, look, it's coming out. It's coming out. I'm moving forward in time, and it doesn't care that the anode is up there. It's like completely unaffected by it. So that's kind of like the sort of evidence I like to see, and it's able to go through this material here and machine a change in its structure and make something look like it's disappeared, and one would imagine that it's been caught into the structure of the Evo. Um, and it's done that, and I didn't put any extra energy in for it to do that. It's just gone ahead and done it. So, you know, something is going on, and I don't believe it's thermal transmutation or heating or material disruption. Well, certainly if it's not got charge and you can't see it, I'd certainly call it dark matter. Because it definitely has energy within it, and if it's carrying trillions of atoms within its structure, and at some point the confining structure can reveal those atoms, then there's matter and it's dark. I agree, join the technicians. He makes a comment, respect this technology but never fear it. We need to do these experiments with proper precaution, casualty free, for the science to see the mainstream light of day. Yes, I have talked to Norris Peary. Norris Peary was working with discharges. He'd get higher and higher and higher current discharges, shorter and shorter pulses, and then he couldn't go any further, and so someone suggested, let's go and use a microwave. And he then used microwaves, and he was perfecting that technique. And you know, I had discussions with him at the beginning of 2017, and then he suddenly got a disease, was in a hospice, and died. Yuji Bajatov, he died of cancer. Uh, Ken Shoulders, cancer. You know, these things do affect people of advanced years. This is true. But the Russians certainly in 2018 were pretty sure that it was Yuji Bajatov's exposure to high DIDD discharges, particularly with water involved, that could have been the thing that was assisted his demise, let's put it that way. And need I not remind you of Leclerc, because I do believe cavitation systems are the most dangerous, like hydrosonic heater generators and stuff like that. These are by far the most dangerous devices to be researching, because we have shown, even in subtle ones, in the cavitation of a Marsa, that you are producing strange radiation tracks, and there's more data to share both in the Marsa vibrator and the Marsa gas, and it will become very clear that these things are transmuting. I think there's many more people dying from driving a Tesla. So, I think the pioneers have put the information down. The volunteers right now are showing extremely interesting data that is verifying the pioneers' work. I know Matsumoto has selected. I selected a whole bunch of papers, and Matsumoto is painstakingly translating those into English. So I do believe that we will have some of these papers available. One of the papers I asked for was a new type of electric current, and also another paper that was a new type of magnetic current. So he observed something that led him to give those titles to those presentations, but they were only in Japanese, and so we will have those at some point. And then also there were things to look at nuclear remediation. And what is nuclear remediation? That is technologically accelerating the decay of radioisotopes using ball lightning. And it's specifically saying that. That was only in Japanese, and it's not in the book that I have, but we will have those hopefully soon. It is Pandora's box, but it's a Pandora's box, in my view, where the nasty stuff has already been put into deployment, let's put it like that. And I would want to see the positive aspects of the technology available, so that we're not strung on, unnecessarily with technology that really is that is just embarrassingly backward. Shoulders very specifically is saying in the presentations that I shared tonight that you are getting a net gain in energy by just mass rectification, by essentially shielding mass and either forcing it in a particular direction or let it eat mass and then cause the confining structure to break up and spit the mass back in another direction. And so it's mass rectification. So it's by shielding mass, you can gain a net momentum, and then if you can do that, you can generate power from that. But secondly, he has a way of generating energy, which is as the evos are condensing and forming themselves, they emit 2 electron volt photons, and these can hit a traveling wave tube, and they emit more electrons, and these can feed the the evos, and so it's a self perpetuating loop. So you basically have the discharge unit here, the anode here, and then a tube which is at half bias, and as the evo travels down, it's emitting these 2 electron volt photons. They're emitting more electrons, that goes in and condenses, and so on. So you then have all of these also additional electrons that don't become part of the evo. They're traveling through towards the anode, and so you get a net gain of electrons going, and that is when the evo finally hits the anode, it needs to gain thermal energy back to reconstitute the electrons. And so you are converting some forms of energy into other forms of energy, but in no point in that is the what do you call it, 0 point. It's not to say that 0 point isn't involved. It's just I've given you 2 examples where Ken Shoulders is accurately, in my view, describing methodologies by which you can gain work for free by leveraging what evos are doing and effectively rectifying their action. Yeah, shielding is very important, and particularly for water arc. Right, I am now 1 hour 37 minutes past curfew, so I'm going to have to try and get back past the police station. It's going to be fun. After I've packed up. So I'm going to probably have to bid you adieu. I will, as I said, add links, and I will add other video clips, GIF animations, and full quality segmented videos, both at real time and in probably 1/30th speed. for you to analyze at your leisure, as I described earlier. If you want specific things that you've seen in here, links or whatever, just ask me questions in the section at remoteview.icu. Anyone can ask questions there as that particular newsletter is set up, and I'll endeavour to answer them. Yeah, I think we can terraform some planets. I'm not so sure about the moon. I'm not sure it's got enough uh, ambient pull of whatever it is that causes gravity in order to maintain its atmosphere. But certainly, you could make the atmosphere and have it encased in a dome. Um, Mars doesn't have enough gravity to maintain a dense enough atmosphere. So on Mars, you would again have to either evolve to require a lot less oxygen, or walk around with oxygen generator on you, or in structures that would allow you to work. I mean, rather than building structures, you would be better off using exotic vacuum object mining technology to bore tunnels and create holes under the surface. And in those holes under the surface, which are hermetically sealed, you would then build your atmosphere, and you would use EVOs to control your environment and produce the lighting that you need, and the cooling, the heating, and whatever. I think it would be easier to bore and make a civilization actually under the surface than try and build stuff above. You want to really use this technology, perfect it to travel to other solar systems that are already Earth-like masses and inhabitable zone, and then you're going to have a much easier time. Yes, cloaking device. Yeah. Well, my voice is like this. Can you sing some Frank Sinatra? Fly me to the moon and let me be among the stars. How about that? Yeah, happiness, maybe. Okay, so thank you very much for your time, and I did it my way. Bye.